Thank you. The floor is yours. Thanks very much for.
I started the recording.
Yes, and we are recording so that you can share this presentation whenever you want. Okay, thank you very much.
Okay, folks, thank you for the introduction. First of all, everything is still working? Yes. So yes, the word influencer has not been applied to me to my face, but I guess if you have 1,000 followers, then you are technically qualified, so no problem there. Yes, I am happy to be talking to you, and I readjusted my slides a little bit for the topic of the meeting you guys are having. And it will be a personal story, basically, how I got into this. Hope you find it interesting. And some of the content will be relevant to literally what is happening the past couple of weeks. So this is also hopefully engaging. But before, I would like to get through a few slides, which I always show for the past 3 years, because, well, I am originally from Ukraine, but it's not even important to support Ukraine, to be related to Ukraine. But this is a picture of my friend Ksenia Minakova, who is a professor in Kharkiv, and she is sitting in what used to be her lab. And this is her sort of trying to salvage some of the equipment out of the lab. Her lab was actually hit twice or maybe even 3 times. This is the reality. But we are trying to do something to maintain and preserve science in Ukraine, because if we start from scratch after the war finishes, it will be very hard. Historically, Ukrainian science is very strong, and we want to keep that kernel alive. So one of the initiatives we have is we collect used equipment, and we are figuring out a way how to transfer it to Ukraine. So you can see some pictures of the equipment that we collected already at the University of Pittsburgh, and we want to scale this scheme up with some support from American organizations. And I know there is a bit of effort like this also happening in Europe. Another thing, of course, related to political situation now in the US, it is very pertinent for American scientists, but this is a project actually out of Europe, where a professor for political science, Pascal Laborier, partnered with a photographer, and they made portraits of scientists who had to go to exile. And of course, Americans are not really threatened by this by and large, but in other countries, including Ukraine and even Russia and many places like Venezuela and places in Africa and around the world, scientists are prosecuted or they have to flee due to the war. And these striking portraits, we are displaying them now in Pittsburgh, but also this exhibition is traveling through Europe. So you may catch a glimpse of it at some point. Keep an eye for it. Also, open and sharing is an idea I embrace at many levels, including sharing the infrastructure for research. Each university invests many millions of dollars in shared equipment or just scientific equipment, and a lot of this equipment is locked behind closed doors and labs, and I've been always a promoter of acquiring equipment that can be shared between many users. And so we are creating this lab which is aimed at Western Pennsylvania, and it gives access to measurement and fabrication equipment similar to what I use for my research. So this is another way we can share. And I know that in Europe this is much more widespread, but in America, these shared centers, in my experience, are more rare. Let's see. Yeah, and finally, my own lab, we do low temperature measurements. So these are some dilution refrigerators you can see on this slide. This is the University of Pittsburgh. We have a very tall building. But we are not in this building. We are in a building behind it. We also make nanoscale devices in the clean room. And then we measure them at millikelvin temperatures, sometimes in the presence of magnetic field. And sometimes we also use microwave measurements like people do for qubits. And sometimes we do just electrical transport measurements. If you want to learn about the process of how we make devices and measure, you can try to find this movie, How to Build a Quantum Computer, which I made. It's a kind of a funny movie, but it goes through the process pretty accurately, just, with some jokes, basically. And finally, before we jump into it, I have to acknowledge the collaborators that we have that grow the crystals that we use. So we make nanoscale devices, but we don't grow the crystals. And the crystals come from Europe, including some in Italy, and also from the United States. And they are nanowires, two-dimensional electron gases. And majority of these crystals are semiconductors of very high quality. And then we incorporate them with superconductors and things like that. Okay, thank you for staying with me through this. And now I want to tell you, like I said, a personal story that stems from my own research. Of course, this is also a very proud Italian moment because this theory was developed by Majorana in the 1930s, where he was solving a Schrodinger's equation in a relativistic regime called the Dirac equation, and he found these solutions, and each solution of this equation can theoretically be a particle, which is its own antiparticle, which is unusual for fermions. So ever since, we are trying to find Majorana fermions. There is a neutrino search for Majorana neutrinos to prove that neutrinos could be Majoranas. And in condensed matter physics, where I work, there is an analogy. Some of the similar math is used to describe states, modes, really, in systems of electrons that behave a bit like Majorana fermions. They can be their own antiparticles in particular. And this is interesting from the physics point of view. I think is one of the most interesting topics currently in condensed matter physics. But it is not real particles like neutrinos, it's composite particles. And so my own interest in it really is fundamental, but I have to admit a lot of interest and a lot of what fuels my own lab with support comes from the idea that these objects represented by blue and white circles here could be used for quantum computing. And this quantum computing can be done in a way that protects against some of the noise, which is a big problem in quantum computing, decoherence. And so the reason why this is such a viral idea, I guess if I'm an influencer, I can use cool terms like viral, and I guess I should also use vibes. So it has weird vibes, but it's very viral. Because of the math, how you transform from bosons to fermions, these objects are connected through invisible strings. And these strings are represented by red lines in this plot. And the universe kind of keeps track of how these strings move in space. So if we move in time and we move Majorana modes around each other, we introduce twists, or they're called braids, into their world lines, their trajectories in time and space. And the twists are doing computation. That's the idea. It's very cool. It's a very cool idea. The limits of how it can be applied to real quantum computing are debatable. Maybe the sales pitch falls short of the reality of how this computer will actually work if it's ever built. But this is the idea. And then the idea is that if there is this noise, I don't know if you can see my mouse, but hopefully you do. And so on the right-hand side, there is this noise. And if this wiggle doesn't untwist the knots, then computation is robust. And robust quantum computation is what the entire field is after. This is the idea behind error correction. Here, error correction is maybe not needed or reduced. And so this is very attractive. Now, how is it relevant to me? Well, some time ago, 2012, we published this paper, which is a very famous paper. We said that we may be seeing some evidence that such Majorana modes could be realized. And, you know, there is a word signatures in the title, which at the time we thought was a way of being very cautious. Of course, you know, in subsequent publicity and communication about this result, this word was rarely mentioned. And for a while, basically, people said, oh, the discovery has been made. But the device we made is this nanowire. So the object that is diagonal in these pictures is a semiconductor nanowire of indium antimonide. And on top of it, this greenish shape, we put with nanofabrication a superconductor electrode, and the combination of semiconductor and superconductor, a one-dimensional semiconductor. And then you have to apply magnetic field, pretty large, 100 millitesla or even more. Creates Majorana modes at the ends of the system. So to represent this, I don't know if you can see it, but at the tip of the nanowire, we snuck into the cover of Science a portrait of Majorana himself to represent that Majorana is appearing here at the end. And so this is a pretty simple theory that predicts that Majoranas will appear here. And so in principle, it can be demonstrated. It's a one-dimensional, non-interacting Hamiltonian that can be solved by an undergraduate student to convince themselves that Majoranas should be there. Of course, on the experimental side, there are challenges because of the nanoscale nature of this object and the uncontrolled environment around these nanowires. But closer to what we are talking about today and open data, I personally came to this from a very optimistic point of view that if we share data, then other people will interact with these data and they will have their own ideas. And so for this paper, I thought it was particularly important. I was a postdoc at the time, but the whole team agreed to provide raw data for just the figures of the paper so that people could download these files. And then we also had a bespoke software called SpyView written by very talented Gary Steele, who is now a professor at Delft, where you could visualize the data and you could sort of take line cuts, you could change the colors to see the hidden features that may be not apparent in the color scale chosen in the paper. You could apply certain mathematical operations to the data. In the list, you can see some subtractions, and you can take derivatives and offsets and stretch and so on with the data. And so if you are, for instance, a theoretician thinking about these data, you could get these files, install this software, and understand deeper what was measured. And this was the idea. And this was 2012, and nobody was doing this in our field. So it was you know, I was very proud of it. And also we were given an opportunity to give a lot of talks at the time, because if you have a famous paper, people tend to invite you. And then there was an opportunity to promote also this idea that, look, you can download the data and you can explore it. So this is a very natural, right? You're a young scientist, you want to interact with your community, and you want to give them access to really the depths of the things you measured. And also, like I mentioned, these nanowire devices are quite rich. Even the control knobs of this device were about 10, because there's different electrodes that you can apply voltages and magnetic field, source drain bias, temperature. So in this 10-dimensional space, you could take a lot of data, and you could take different trajectories, and other people could have other ideas for what you could measure, or have other interpretations of your data, which indeed happened, although perhaps not as a result of us sharing the specific data, but it did happen. And what happened was, okay, I'm going a bit up. What happened was this discovery was basically disproven. Okay, so there was this moment when everybody thought we discovered Majorana modes in nanowires, and then now I think probably nobody believes that. And so fast forward more than 10 years, 13 years, I am now this type of person represented by this meme. I don't like to submit to Science, Nature, or PRL, which has the mission of moving physics forward. But I prefer, although not rigidly insist, that we submit our papers to SciPost, which is a journal governed by community, by physicists, run out of Amsterdam. And that all the data are deposited on Zenodo, full data, right? So in the paper in 2012, it's the raw data of the figures. And now we share full data. And of course, our primary and first paper, first and foremost, goes on archive. And then when somebody has the time, it is submitted to a journal. So how did I get from publishing in Science, wanting to do that, thinking that that's very important, and sharing data for the benefit of community, to sort of rejecting the mainstream journals as much as I can, and then demanding that all data be shared, and so on. It starts here. Like I mentioned, my slides are a bit out of logical order, but the measurement we did was an electrical measurement where we sent current through this nanowire. So the purple is a nanowire again, and this bluish is a superconductor. So Majorana modes are expected here as stars. And then this left side of the device is essentially a measurement apparatus, because this is not a superconductor, and the electrons have to go through the nanowire, tunnel over this tunnel barrier, which is a green thing. And then if there is a Majorana, the idea is there's a bit of extra current. And so this manifested in a zero bias peak here, a little bit of extra current at the symmetry point in the curves, which is where Majoranas are expected, at the symmetry point between sort of matter and antimatter, or particles and holes, antiparticles in the middle. And this is a color scale. So this is from the science paper on the left of the original one. These are some of the papers from my own group. And the bright streak in the middle of the blue figure is the zero bias peak that we study as evidence of Majorana. So what happened was, like I said, there were doubts about this explanation expressed a few years later. We continued to investigate it, but in the meantime, a big company, Microsoft, became very interested in these results, and they put a lot of money. They hired a lot of physicists who were working on this, to work for Microsoft. And I don't know if you've seen this publicity, but at the beginning of the year, in January of this year, 2025, this process culminated in Microsoft announcing to a huge fanfare with articles like in the New York Times and other very big outlets that they have created not only the new state of matter, this topological superconductor, but also they have created a topological qubit that you can see here at the bottom. And you can also see this YouTube video that they posted is very well received, 4.7 million views and probably growing since then. And it's path to 1 million qubits and so on. I don't know if you know who this person is. I hope for your own sake that you don't. But this is Senator Ted Cruz, who is having in his hand in the US Senate around the same time this golden chip that Microsoft has introduced and which has allegedly at least one, but maybe up to 8 topological qubits, and each topological qubit requires 4 Majoranas or more. So this would be up to 32 Majorana modes that Microsoft says they are controlling on this chip. And well, if you don't know who Ted Cruz is, you may know some of these people. So Satya Nadella is actually a CEO of Microsoft. And he had a very optimistic post on X, formerly known as Twitter. And you probably know this person at the top of the screen. He is also quite famous and is a big enthusiast of quantum computing as well. But of course, it's not about hyping tech. It's about building technology that truly serves the world. This is a quote from Satya Nadella's X post. Now, I mentioned to you that there are doubts about this discovery, and these doubts you can see already even on X itself, because still the mechanism of community added notes works. And I am not on X, so I had no part in formulating this note, but you can see that readers added some context to this communication. And you can see that paper published in Nature does not support the claim that they have created a topological qubit. So this should already give you some sense of, wait a minute, there is a New York Times, there is a US Senate, there is Elon Musk, and then there is Nature article that does not support that there is a topological qubit. What's going on? Pushback is not just on X. Here I have collected just the publications where they talked to physicists more extensively, and those predominantly express various degrees of skepticism, from physicists question the Microsoft claim at the Wall Street Journal to Microsoft quantum breakthrough labeled unreliable and essentially fraudulent. I have to say that's probably quoting me, but I am not the only person by far interviewed in these articles. And so there has been some pushback to the notion that this big discovery has been made. And this is fast forward 13 years from when we originally thought we made it. And now we are still at this stage where we're questioning it. Now, let me tell you a little bit about the physics behind it. Essentially, what we want is this situation at the top, where Majorana that we're looking for is a kind of a wave function that has two parts, the left part and the right part. And in a nanowire, we have on the left half of the electron and on the right half of the electron. And in this spatially separated electron, we can store information, a bit of information. And as long as the green and the red wave functions don't overlap, this information has some degree of protection from local noise. So if one wiggles on the left or the one wiggles on the right, this bit of information will not be lost. It will not be flipped or erased. Now, realistic situation could be that suppose we have split the electron into halves, but not enough. Due to disorder or due to the nanowire being too short, there is overlap. What happens then? It's like particle-antiparticle annihilation. The left and the right overlap, and the quantum state starts to oscillate between two possibilities, and the bit starts to rotate or flip. So this is just like decoherence, which is the problem of the qubits. Now, the shocking finding, well, it was shocking 10 years ago. It has been quite a long time since then, that another Italian, actually, Professor Dr. Silvano Di Franceschi, who works in Grenoble right now, found that even if you don't split electron at all, if the two halves of the electron are completely overlapping, and it's just a standard electron trapped inside the nanowire, its wave function can still show the same signatures as we expect from Majorana. And this is a work of Silvano De Franceschi on the right, and the bright streak in the middle is this effect that he found in just a conventional, what is called a quantum dot, coupled to a superconductor, not a nanowire, not a one-dimensional object, but a zero-dimensional object. Put an electron there, and it produces the same signature as on the left. This is a paper, another paper from 2012, where they show the same feature in the middle, a little mountain in a three-dimensional representation that is a zero bias peak that they ascribe to Majorana. And a couple of years later, we learned that it's not. Okay, now let me pivot a little bit. So far what I told you is that there is an interesting topic that many people are following. It's called Majorana zero modes. I, due to time, did not have time to explain all of it to you, but if you go to my YouTube channel, you will see a lot of me talking about Majorana and explaining the measurements in more detail. But it's a topic of attention. Now, I'm also a little bit proud that we shared the data early on. And since then, we shared full data from 2012, which is on Zenodo. So you can go and see what we measured and build your own theories. And that was coming from the place of we want others to participate in our research. We want more brains thinking about our data. We want that, and we welcome that. And something happened in between where now we have a big company claiming again and again this discovery, and the scientists are being skeptical, labeling it with bad words like unreliable. Something happened in between. Right, so what happened was it was clear that the science has at least two interpretations, and probably the trivial one is the more likely one, because it's easy to localize an electron and it's difficult to split an electron. But the claims that this is Majorana, here is Majorana, there's more Majorana kept coming. And it may have to do with the fact that Microsoft is putting, now a Wall Street Journal reported $300 million into their quantum effort, and it is centered around topological qubits. I was working in this field as just already a professor, and we were not getting the data that would tell us, yes, there's more and more evidence of Majorana. We were getting data that was saying either no further evidence of Majorana or evidence against Majorana, but other people kept publishing. And so at some point I said, well, folks, can I see your data? Because I am not getting what you're getting. Can we compare? I'll share my data, you share yours, and you say you have Majorana. Let's have a look. Let's have a look. And well, it was my former group in Delft, so maybe because of that, but they did share a little bit of data with me. They sent me a PDF with the pictures of the data, and we started comparing it to the paper just to map out. This is figure 1, this is figure 2, this is, wait a minute, where is figure 2? We couldn't find figure 2. But we found a similar plot. And then I said, yeah, that's probably they just scanned many times and it's just a figure 2 is just, you know, is something like that, just they didn't show us the right data set. But then my friend and colleague Vincent Maurik, who is a first author on our science paper, by the way, looked closer, and the graph that looked similar had the same noise as figure 2, but it looked different. And so we figured out that that was the data, but they cut out some pieces and they stitched it together, and that they made the figure 2. And it looked like it supports Majorana much stronger because they were claiming quantized conductance. So what happened, fast forward, 2 papers got retracted from Nature. We brought up concerns, and you know, these concerns had a certain effect. Eventually, there was a lot of back and forth that I will not go into, but there's also further action pending on a number of other papers from this project that we are still pursuing. It takes a long time, years, to get this action going. And just to illustrate the problem to you, here is one of the ones that I find easy to explain. So the paper, that retracted paper, Quantized Majorana Conductance, has this statement in the paper: notably the ZBP height, that's the signal, zero bias peak height, comes back up to the quantized value. Quantized value is 1, it's the dashed line, and does not cross through it. So Majorana physics allows it to be quantized or below. It cannot be above. So we cannot have anything above, much above the red line. And of course, what they show in the paper is the orange data points. And then when I got additional data from them, right at the point where the graph stopped and was cut, the data continued. And it just goes above 1, and it goes up and up and up, and all the way to 1.5, which is in direct contradiction with the Majorana physics hypothesis. So this is how fuller data allowed us to find one of the problems with this paper, right? And so at this point, it became a matter of, okay, I am sharing data so that other colleagues could engage with my experiments so that we could work together. To here, it became, wait a minute, how can I even trust the claims in a paper if there is no data that I can see behind the figure that is in the paper? And this is not just for Majorana. In my experience, in my field anyways, condensed matter physics, oftentimes if you dig in, you will hit some questions. Now, it may not be something like, oh, let's retract this paper, but you make this claim like, I don't know, all the samples look like this, but you say you've measured 30 samples. Can we see the other 29? And maybe it is not so beautiful. And this could save somebody a lot of effort, because suppose I want to get into the same line of research and I see, whoa, beautiful results, but I don't know that it was one sample ever measured. And so I hire a postdoc to do this, and the postdoc hits the wall, which is something that happened to me in another project. Now, here is another one. This was a cutout that I told you, oh, they just cut the data and didn't show the rest. This one is a kind of more of a selection. So this is a science paper from University of Copenhagen and Microsoft Research. And the beautiful data here on the left in kind of purplish colors is showing a superposition of two effects. One is this black shapes which form a wiggle. This is a well-known Little Parks effect known from 1960s in superconductivity, where superconductivity comes and goes depending on magnetic flux in a cylinder, which here is a nanowire is a cylinder. And the other one is bright streaks in the middle of the graph. That's again the zero bias peak. It should be familiar to you from the other examples. And the amazing thing is the coincidence. The Little Parks oscillations coincide with the streak, and the streak is at the odd Little Parks lobe. So at phi naught here. So the message of this paper is you don't need to worry about electricity, electrostatic potentials, just dial in the magnetic flux, and as soon as the flux is quantized at the value 1, boom, Majorana modes appear, and this is very easy then to scale up to make more and more of them, what you need for qubits. So the paper got into science. Now, we also got some extra data from this paper because it looked implausible that it works so beautifully. It's too good to be true when you read the paper. Of course, this data we got with the help of the editor of science. In this case, the editor helped. In other cases, the editors didn't. But the authors of the paper refused to share data, and they are still refusing to share data from 7 more papers. So just no. But for this paper, we got quite a bit of data. In fact, this summer, they shared 11 gigabytes of data after first saying that we don't have any more data, after giving us 50 megabytes. So from 50 megabytes to 11 gigabytes, which still fits on Zenodo, by the way, we have a lot of data, and we keep looking at the data. So here in these patterns, you see, this is the interesting regime, this lobe. Do you see my mouse? Hopefully you can see that.
No, sorry, we don't see your mouse, so you'll need to describe better. Yeah. Sorry about that.
How about now?
Still no, I think.
Okay.
I can see it on my laptop, but we don't see it on the projection.
Okay. Yes, exactly. Yeah.
So in the bottom row, you see 3 examples from their data that they shared, where there is again this pattern. And in the middle, you have an empty region, like black or dark blue oval. And on the sides of it, that's where the zero bias peak should be. But in the left one, which is in blue, red, white, you see a split peak. In the middle one, which is in red and gold, you see a fork, peaks coming together. And in the last one, you see just nothing. States at very high energy. So all of these examples were not shown in the paper, but they would cast serious doubt on the message of the paper. And what's more, here we have panel E in the upper left is the gate dependence to show that, look, no matter where you set the gate, left and right, there is a zero bias peak feature near 0 at all gate voltages. So it's independent of the gate, but it is dependent on the flux. But in fact, what they showed is a very narrow range of gate, and immediately outside that range, there is no zero bias peak, right? So they just cut again the data, or they rescanned the data in such a way that any weird features don't fit in the graph. They are outside. So what I compare this to is this example, where here you see me a little bit younger, and well, I am flying. This is human flight. This is what, the ancient Greeks were writing about. And, this I think should be also a science paper, because nowhere in these pictures you see a person touching the ground. So this is something like to illustrate what this science paper is that we were investigating. Now, let's see where we went. We went from wanting to interact with our community and sharing data to investigations, research integrity, denied data requests, and all kinds of systemic failure where journals don't know what to do, universities cover up, government is just sort of standing on the sidelines. And it's not like I had to go out of my way to find these examples. These were just some of the biggest actors in my own field, but I only looked in my own field. So this is how we get back to this meme, right? This is how I say, look, yes, I would like to interact with my colleagues in an open way, but it begins with trust. I just simply, in order to trust them, I need to know what their data look like, more complete than what they put in the paper. So I am not a policy guy. I am not fond of sort of being on some committees that decide what is fair data, how we should do things. I just have my thoughts, but I did put some effort in organizing. And one of the things we did with support of the NSF, this conference in Pittsburgh, where we gathered a diverse group of people, of course, scientists in condensed matter physics, experimentalists and theorists, but also representatives of journals. We had an editor of Nature, we had an editor of Science, if that impresses you. Certainly they have a lot of influence. We had executive editor of APS, of all the physical review journals. We had lawyers, we had government representatives from the people who check this stuff. And we talked about the topics that you see on the screen. And so I'm proud that this conference resulted in a number of products. So oftentimes people get together, they all agree, and then they part their ways. We wrote a report, and hopefully this is coming out as a special type of article in Physical Review B. But here you can see on the right a list of authors, and on the left you see recommendations of the report. And so they are split by group, recommendations for practitioners, for scientists, recommendations for publishers, recommendations for universities, and a little bit for government. And throughout these recommendations, now this is 25 co-authors, but also informed by discussions of 50 to 70 people at the conference, not all of whom were co-authors of the report. Data. Sharing data, access to data is a foundation of enabling reproducibility of our claims and reproducibility of what we claim in the literature. Replicability is a foundation of prosperity in our field, a guarantee that we can keep delivering amazing breakthroughs that sometimes power our society, like hard drives and MRIs and satellites and lasers and so on, going forward, right? Maybe it will be a quantum computer, maybe it will be something else, but without reproducibility, we will either get there slower or we will never get there, because we will just be fooling ourselves that, oh, we made all these great discoveries, that if you dig, some of them will turn out to be fairy tales. So I encourage you to read this report. It's on arXiv, and you can follow some of the recommendations, see if you agree with them. Also, please provide your feedback to me and the other co-authors. We would love to engage on this. This is just the first such report, right? We can get together again and see how much progress our community has made. But another thing we made is we made a movie. And this is about half an hour, which as an influencer, I've been shamed in the comments that is way too long. It should be more like 45 seconds. But we are a bit old school, but it's a professionally produced movie where participants of the conference discussed. And you can see here, Jessica and Carl are more of the editors, who I had nice snapshots of, but You hear from people who investigated some big things. For instance, James Hamlin, who one of the people found room temperature superconductivity from Rochester problems there, and led to also 2 nature retractions. And you have people from Würzburg that found some of the other Majorana issues with angel particle Majorana from UCLA. So you see here from whistleblowers, you see from very respected scientists like National Academy members and members of the Presidential Council. And you see just from young scientists who experience some of the effects of unreliable research and what they think. So I really encourage you to watch it. Maybe if you're professors, you can show it to your students. If you're students, I'm really sorry that it's a whole of 34 minutes long, but perhaps you could spare at least a fraction of the time. I'm told you can fast forward the first 8 minutes. Also, there is, there is goodwill in the system to also talk about reproducibility. For instance, we are having this paper coming out in Science, and it's about striking patterns from different experiments. There's 4 different experiments that you can see on the screen that are all done by my students in my group. Sometimes in an attempt to look for an interesting effect like Majorana, sometimes in a specific attempt to replicate a signal that is looks amazing but can have another explanation, like the zero bias peak in the upper left that we already talked about, and there is some of the other effects. And here I would like to mention the last one, the 1/3 charge jumps, because like I advertised, it is relevant to what happened just recently. So the idea here is that there is some pattern, these bright lines, bright blue lines that become red lines that go diagonal. And these are, as you cross one of these lines, you add an electron to an island, a semiconductor island. And then the yellow lines marked by 1, 2, 3, 4 are kind of shifts in the regular pattern. So you can see you follow the line from upper left corner, and as you cross the line labeled 1, the dashed line, all of the blue lines jump. And because this device is sensitive to charge, the interpretation of these jumps could be that another charge is added to the system. And because it's a fraction of the period, in this case, somewhat close to 1/3, between 0.4 and 0.29 is the shift. The interpretation is that this is a fractional charge, which is potentially a 1/3 charge. So like we're adding 1/3 of an electron. And 1/3 charges are well known for 40 years from fractional quantum Hall effect. But there is this interesting interference effect that if you run electrons around the fractional volume, then the phase that they accumulate would be proportional to the charge. And so if one more charge is added, the phase would shift by 1/3. And so this interference effect was kind of difficult to demonstrate experimentally until about 5 years ago. A new round of claims appeared that, oh, we see 1/3 jumps. And for these claims, one guy received a Buckley Prize from the American Physical Society just a couple of weeks ago. So the community, some kind of big people gathered on the committee and said, finally, this 1/3 interference, this shift has been discovered, established, and even a prize has been doled out. But our paper that is coming out shows that you can get this fractional charge with trivial effect, that if you have an island called primary dot here in the middle, and then there is another dot that is dashed, a side dot, that is unintentional in your device, and there is a capacitor between them. And this capacitance is, let's call it 1/3. So when I add one whole electron to the side dot, it induces a potential equivalent to 1/3 on the primary dot. And this is what is responsible for the 1/3 shifts in our data, right? Now, I don't know about his data, but I did ask already some years ago. I wrote to him and said, well, I would like to see more of your data because working with semiconductors for many years, how your data look. Am I still with you? I had some interruption here.
Yes, the communication stopped for 10 seconds or something like that.
Yeah, so basically I asked for data, and this professor, he refused. He refused to share data. And of course, at that point, my suspicion goes to 11, to a higher level. I cannot say that he has not made this discovery, but I can say that I can get this data without fractions charges, and I can say that he does not share data. And well, you can discuss whether such a person deserves a big prize like Buckley Prize, which is considered a precursor to the Nobel Prize. Okay. Now I have to regain my ability to change slides. Now, not to scare you too much, but here is another thing that is already available to you, and I played with it already a year ago or so. I downloaded the real data on the left, which is from Delft University, and it shows these beautiful crisscrossing shapes that go like this from bottom to up. And at the crossing point, they just split. And these are, again, some states in superconductor, semiconductor structures like the ones I study. And because they don't stick together, but they split, they're definitely not Majorana. They are trivial quantum dot states. And this is just data that is beautiful, but not a breakthrough. And then I asked ChatGPT, and with a few prompts, you can see in the middle, at the crossing point, added this zero bias peak. That is a vertical line that you can see very dramatically because it kind of patched in artificially inside this data. And then on the right, you see I asked it to change from Lorentzian shape to some other shape of the peak, and I literally asked it, can you blend it more in the background so it doesn't stick out? And it already looks much better. And so if we focus on the graph on the right, it is actually that at the crossing point, the gap in the system, the excitation gap, the energy gap, the fundamental bulk property is closing, then it is reopening and leaving behind a zero mode that is stuck to zero bias, as Majorana should. So this demonstrates a topological phase transition with reopening the gap. And only a few pixels have been modified from the original graph. And then I asked ChatGPT to deliver back to me in the same format the data file that I loaded, and it delivered it back to me with the modified pixels. And so this modification will be basically impossible to detect with any AI detection software because most of these data are real, obtained from a real device. And so I played with it more. You can see here some examples where I synthesized the qubit data, Rabi oscillations on the left, quantum dot data, Coulomb diamonds on the right, and I added some realistic features like noise, charge jumps, and so on to convince any referee that you like. Now, some of you may not be surprised by this. Some of you may be completely shocked and freaked out because in principle, I can fabricate 5 figures of a Nature paper over about 1 hour of prompts with ChatGPT. But the good news is that ChatGPT kind of decoheres itself, right? We all know the hallucinations, it loses the train of thought, it forgets what you asked it. And so to synthesize 1 GB of data like this, that is consistent and it will look like it came from the same device, is, at least at present, it's impossible. I can synthesize 5 figures for a paper, but I cannot synthesize the whole experiment. And so if you ask me to share full data, I will not be able to. And so here again, a very simple solution is to just show your data. And then this problem of AI will be at least reduced. But there is always the next circle of adaptation, of course. Now, what seems natural to me, now let's talk about what can be done. All the examples I showed you, all the things I talked about, come back to having data and sharing data. So it starts from just having data, right? And sometimes I write to some famous people, not to check their data, but to build on their data. We had an interaction with somebody where we wanted to extract some values from their data to inform our numerical model. And somehow they seem to have genuinely not kept track of their data. They just said, oh yeah, this was, whatever, 6 years ago, and I don't know where that server went, and the postdoc graduated, and we can ask them if there is data. And to me, this is very funny because all the way from my PhD, which was 25 years ago, I have all my data on the hard drive. And I cannot take out the notebooks from the lab because they need to stay in the lab. But when we had physical notebooks, I illustrate by this picture, I cannot take the notebook, but I'm allowed to take pictures of the notebook. And so I kept all my notebooks in digital form from my PhD, from my postdoc, and eventually we switched to PowerPoint files, which I also have. So you have all your data. Then, as actually was already mentioned, additional data available on request just doesn't work because either they say your request is unreasonable or they just sort of decline, even if it's mandated by government codes, by ethics standards of the university. They just decline and there seem to be no consequences. So this just doesn't work. Finally, I think Zenodo was already mentioned, or you will interact with Zenodo, but it's a wonderful service. Again, from the physics community, it is created by CERN, and it gives you 50 gigabytes per record. Our largest experiment, the totality of the data obtained over months is several gigabytes, maybe 2 or 3 gigabytes per experiment. And so it's plenty of data for us. And we have started sharing from every paper. You can see Frolov group workspace community on Zenodo. And before my paper goes online, I require my student prepare a Zenodo repository, and then it goes on archive, and then we send it to some kind of journal, which my preference is SciPost. So what's inside each repository? Everything. First of all of the data, right? You can make a separate folder for figures, but then just the full data, the way it was obtained, all of the logbooks. So that's the detailed journal. And then any summaries, like if we had group meetings and we prepared a bit of data with some comments, and then if I gave talks or my students gave talks, you can also archive all that. Now, is this in FAIR format? I am not sure. I think it could be improved further, and I intend to organize my work process in my group that we make it more and more fair. But already now, no matter what form you have it, just if you kept it in at least somewhat organized form, we just zip it and upload it. Takes 10 minutes and it's out there, right? So not to make a barrier out of preparing data. People say, oh, it will take me weeks to prepare data for uploading. Well, if that's the case, don't worry about it. Just upload what you have. Nobody will judge you, seriously. Then once you're in the habit of doing that, go to the next step and organize it better, because now you already know, right? My students now in my group, they know this is coming. You will have to upload all of your data. So they are already organizing it in a nicer way that we can later track. And then to each of our papers, we add the following statements on data availability, right? It's not upon request, it's where you can find it. And also, as an additional thing I may suggest, is these duration and volume of study, which disclose how many samples over which period of time, how many data sets were obtained, right? And I think this minimal information very useful even for referees to know that, okay, if I will need to be able to find from 7 samples, 5,000 data sets. And so if I want to look at that, I can request that, or maybe I follow the Zenodo link and it will be all there. They have the option to verify results for reproducibility. And this is it. I guess it's a very moralistic story, although I tried to make it just factual and personal. But if I allow myself one last parting thought, is that when I was younger, I still think of myself as young, but when I was younger, and even in high school, I thought that doing science is something like you get something interesting, you share it with your colleagues, you discuss it, maybe somebody's skeptical, somebody has ideas, we all work together. And this is now called open science, but I thought of it as science. I thought that what we call open science was how science was done. And this other thing that I learned to call science through rejections from journals, from needing to apply for grants, from trying to lobby myself for fellowships and nominations, with impact factors and data available upon request. This is what is called science. This is actually not science. Right? And this idea that we need to deliberately open up science is unnatural to me. To me, what is natural is let's just do science with our students, with our colleagues that are willing to do it. Let's just share what we find, have open discussions. There may be a little bit of bruised egos if somebody disagrees, but as long as we maintain respect for each other, we should be able to do some pretty good science. So with this, I leave you. Thank you so much. I don't know if there is any time left. I spoke a bit too long, but I really appreciate the opportunity to talk, and I wish you a good datathon. Thank you.
Thank you very much, Sergey. Just please stick with us for a few seconds more, because now the floor is open for questions if somebody has some. I think maybe Daniel has something to ask. So yeah, well, I'll start breaking the ice. In your very inspiring slide with the meme about what you like and what you don't, you said that you try, if you don't have to not publish on big journals. Do you have a few words on how it impacted your career? I mean, you still managed to
absolutely.
go from postdoc to a very successful professor, but...
Yes, very good question. So I should say, first of all, I evolved into this view from a very secure position of a tenured and fully promoted now professor with a lot of funding and already a lot of nature and science papers. So I risked very little of my own because by now people know me and they might even give me more money just because they know how I do science and what I'm interested in. So this is very fair. a very fair question. So I had to address this in my group, and what I suggest to my students is that I will work with any journal that you prefer and would like to try, right? So if somebody in my group wants to try PRL or Nature Physics or whatever, I know how to try to write a letter to the editor, how to write the introduction that is broadly, of broad interest, and try to push this paper in the journal of their choice. If they don't have a preference, or if their paper is rejected, then I suggest SciPost, and to my delight, a lot of my students say, yeah, let's just go for SciPost, and they're quite happy with that. So that makes me very proud also of my students.
Okay, thank you very much. And anybody has anything else to ask to Sergey? So, yeah, come close. Wait a second. And
hi, thank you very much again. This is more a psychology maybe than science question, but when you see these examples of like data cropping in such a brutal way, I always wonder how can you do it? Because when you see it from outside, it's such a blatant misconduct that you say, I would never do that. And I think everybody that sees it, I would never do that. But then it looks like that there's a lot of people that do it. And I wonder, how does this work? Because maybe you've dealt with this kind of people more than I did. So do they do it in kind of good faith, so they think they're sort of improving the story, making the flow smoother, and then they start cropping a little bit here and there, and then they end up just cropping 90% of the figure, or they actually deliberately say, okay, no, I just want to get this paper, so I will do whatever. How does the mind of, of the misconduct, the scientific misconduct works from a psychological perspective, if you have an insight to share? Thank you.
Yeah, thanks for the question. Yes, certainly. First of all, I don't know if I dealt with these people more than any of you, because we don't know who they are, right? They could be among us. But I did think about this question, and it's a very natural one. And I want to say that, first of all, my cat is meowing. I want to say that, first of all, it's difficult to know in each case without a lot of investigation, and universities typically try to reduce the investigating and find some kind of minor reprimand that they can issue. So without, like criminal level investigation, it's hard to get into the mind of each person. But you described it very well. I think it's basically a continuum. It's kind of a sliding scale, right? It's not like you are a person and you have two paths in front of you. Either do very honest science or do completely bad science, right? You may think you are making the message more clear, even starts in your talk, right? You did a careful experiment, you even described it very carefully in your paper, but when you go out and talk, you simplify so that it's easier to communicate with the audience. Or these corporate press releases in quantum computing are a good example. Oftentimes we see a very careful paper with a lot of details and nuance and incomprehensible terms, and then the press release is like, we discovered a non-abelian state of matter that will facilitate fault-tolerant quantum computing, right? And there's just very little connection to the paper, but and then they tell themselves, oh yeah, but this we do for investors, for publicity, and then we in the corner we do real science, right? And then these lines start to merge because you said it so many times in public that you convinced yourself that, oh yeah, I made all these discoveries. And then there's, of course, people who realize it very clearly what they're doing. So there is a whole spectrum.
Okay, thank you very much. And so does anybody else have anything to ask to Sergey? Or, yeah, in that case, thanks again a lot for intervening, and we'll give you the recording of the session as soon as possible, so that if you want, you can put it on your YouTube channel, whatever you want. And thanks again for being part of this event.
Thanks so much. All right, enjoy the rest of the program.
Okay, bye. Thank you.
Bye.